Thank you very much. It's a great pleasure to be here. It is my first time in Bilbao, though it's not my first time in the Basque Country. And I'm very happy to be here on this cold and rainy day. In England, it was cold and snowy, which is kind of rare there. I'd hoped to give a blackboard or whiteboard talk because we have a lot of really novel results about quantum machine learning. But because we have to use these extremely impressive technologies, which amazingly actually worked so far, I'm going to have to give an older version of this talk, but which some of you might have seen before. I will mention as I go along all the very new exciting developments in quantum machine learning that have taken place over the last couple of years. What is, let's see if I can get this to work. Let's see if this works. Yes, okay. So I'm going to talk about deep learning. Working on quantum machine learning is something that I've been doing for about 6 years now, ever since my postdoc, Patrick Raventros, came into my office and said, Seth, let's work on quantum machine learning. And I said, great, what's machine learning? I mean, I kind of knew. That is, machine learning is the use of machines, computers in general, to find patterns in data and to learn about them, to learn patterns in data. And, but I didn't know how these quantum learning algorithms, how classical machine learning algorithms worked. And when Patrick told me about some of them, he was taking a course in machine learning at MIT, I said, oh, great, we can quantize that. And so we made a series of quantum machine learning algorithms that work in the following way, that if you take your classical data, which is in the form of a gigantic vector in a vector space, and you map it onto a quantum state into Hilbert space, then you get an exponential compression, because if you have an n-dimensional vector, you can map it onto log n qubits. And once you can do that, then you can actually extract features of this data. I mean, famously, you can take Fourier transforms of the data exponentially faster than you can classically. And you can do all kinds of linear algebraic operations. You can find eigenvectors and eigenvalues of large, sparse, or low-rank matrices. To do principal component analysis, you can make support vector machines. Of course, the difficult part is actually mapping the classical data into the quantum state, for which you need either a quantum random access memory or something like that. In fact, this, by the way, I want to say that this, I think, remains in terms of, in this exciting but not yet highly applicable field, as in all things in quantum computing, this is the primary challenge. And if there are people, experimentalists here, I'd like to talk with you over the course of this week. I'll be here for the whole week. About how you do this mapping of classical data into quantum states. But actually, I'm going to talk today about deep learning. So after we'd quantized a bunch of classical machine learning algorithms and shown that you could get very substantial speedups, exponential speedups over the classical algorithms, Patrick came to my office about a year later and said, "Okay, let's look at deep learning, deep quantum learning." I said, great, what's deep learning? And for about a few minutes, I was under the happy illusion that in deep learning that, computers could show us deep things about life, truth, love, happiness, the existence of God, all those things. But sadly, I learned very rapidly that deep learning is just simply the use of deep circuits to try to find patterns in data. And they are deep learning circuits. They've been around for a long time, ever since artificial neural networks were first proposed back in the 1940s by McCulloch and Pitts. The idea is if you make a network which mimics in some sense the way that the cortex of the brain works, that this network can learn patterns that are similar to what the cortex in the brain can learn, which is to say a lot of stuff, because people can learn lots of things. And so I'm going to talk about deep learning. I'm going to ask what kind of patterns can be learned by classical computers and by a quantum computer, and I'll raise this question, which, I mean, I think, again, I apologize, these PowerPoint slides are a couple of years old now, but the same question that I raised a few years ago is still a very important question. So the question is, are there patterns in data that can be learned by a quantum computer but not by a classical computer? And I'm going to talk specifically about the question of deep learning. So if we make deep quantum learning circuits, and I'll describe what these might look like in a bit, are there patterns in data that we can find using these circuits that we can't find classically? And the answer is still, I don't know. I mean, actually, if the data is given to you in a quantum mechanical form, so if the data are the quantum states that are the output of a quantum system, then the answer is yes. We can analyze these quantum states using a quantum computer or even a small quantum information processor to find patterns that would be very hard to find classically. But the real question, and particularly in this day when new quantum information startups are popping up like mushrooms all over the place, is can you actually find interesting patterns in classical data that you can't find on classical computers? So let me see what's going to happen here. So, okay. Oh, this is what I was describing before. Excuse me. I'm very bad at giving these kind of PowerPoint sorts of presentations. Let's see. Okay, great. So, I mean, this is just what I was saying before, that in general we know that there are patterns where, sorry, let me get this out of the way, that if we take classical data, we map it into a quantum state, for example, using a quantum random access memory. I think that this is not working so well. Is there another laser pointer around somewhere? We can map it into quantum states. We can do quantum Fourier transforms. We can do data fitting. We can do things like support vector machines, which is finding the optimum separating hypersurface between clusters of data. We can do principal component analysis. We can find topological invariance of data. We can do quantum finance. Patrick and I have a nice we have a result that basically says we use matrix inversion in solving linear equations to give you, if you're given financial data, such as the history of the prices of stocks on the stock exchange, you can find the optimal investment for a given amount of risk, which is something, strangely enough, that people are interested in. Just that one, okay. Okay, that's better. Now I've got to remember which one is which here. Put this over here. This is a nice thing, and people invest a lot of money in this. Okay. Well, I bring these up because I'm not going to spend much more time talking about this, but the fact that quantum computers can do linear algebra exponentially faster than classical computers means that if we can do this very first step of taking a large amount of classical data and mapping it into a quantum state, then this could be very profitable. However, this is hard to do. So I'm going to talk now about deep learning. Whoops, sorry. Oh, this is actually, I should show you this. This is a, let's see if I can actually do this. So this, by the way, this is a, I will talk a little bit more about this because I just saw this next slide that's there. This algorithm, I'd like this algorithm for finding topological invariance, which uses matrix inversion, you can find connected components, holes, and voids. You can find the topology of your data. This does not require a large quantum random access memory. And let me give an example of how this is currently being used. This picture right here, I wonder if I can actually blow this up a bit. I'm not sure. Well, okay, I think you'll be able to see this. So this is from a paper that applies topological data analysis, the classical version of these algorithms, to brain function. So people took functional MRI data. Each of these little dots is a set of neurons that are talking to each other a lot. This on the left is taken from people a bunch of volunteers, maybe, I don't know about how many, 50 to 100 volunteers, in kind of ordinary resting mode, and it analyzes the connectivity in terms of signaling of the brain. And actually, you see from this that typically you're going, the different colors represent highly connected processes, as you can see. And typically you're thinking about 1, 2, 3, 4, 5, 6, 7 different processes are going on simultaneously in your brain, of which you may be only consciously aware of one at a time. And they have connections with each other, so they're talking with each other. So even your subconscious processes are actually are talking with each other, though they're normally thinking about this in just kind of, in their own little way here. This, by the way, the fact that they're about 7, this is, I believe, related to this feature that has been known for a long time, that the optimal number of, if you have an organization and you're supervising some people, that the maximum number of people you can actually be thinking about is about a time is about 7. So I think this is, this is my graduate student John. This is my graduate student Ziwan. This is my graduate student Oles. This is my postdoc Milad. This is so they're all there in my subconscious battling it out. Okay, so now what is this picture on the right? These are the same subjects. And this is functional MRI data taken from their brain while they were resting, just kind of like thinking about stuff. But this is after they were given psilocybin, hallucinogenic mushrooms. And well, what can I say about the topology of your brain? So this is the topology of your brain. This is the topology of your brain on drugs. And what can I say? It's like, wow, everything's connected, man. They tell me that they're analyzing the LSD data even as we speak. Okay, that was just a little interlude to show you how useful machine learning can be. So I have 40 minutes, right? So good, all right. I just want to make sure I get it right. All right, so how does machine learning work in general? We're given a whole bunch of data, which could be these vectors in high dimensional spaces. Our goal is to find patterns in the data. And there are 2 basic types of machine learning. There's supervised learning, where we're giving a training set where the training set has already associated some kind of classifier labels, C, to each data point, D. So for example, here is a scrawled 5, and the classifier is 5, okay? And given such a data set, we want to find an algorithm that assigns a new data point, D, to the correct class C. So if I'm given a new scrawled piece of handwriting, and it's a 5, I want to assign it to 5. It's a 7, I want to assign it to 7. And there are lots of very good machine supervised learning algorithms out there. And then in unsupervised learning, which is more exciting, but often less successful, you're given data, and now you want to find the classes C that naturally partition the data. So in unsupervised learning, for example, you could be given a sample of a whole bunch of scrawled letters, or scrawled numbers in this case, or digits, and you'd like your machine learning device to naturally to partition it into 10 categories, one of which is 0, one of which is 1, one of which is 2, et cetera, and then be able to assign data points to each category. And there are many different procedures for doing this. Now, before I talk about deep learning, let me just talk about see, again, I'm terrible with these PowerPoint. I didn't come prepared to give a PowerPoint presentation, even if you call this PowerPoint. So, by the way, it's important to recognize that classical machine learning really has been around for a long time. These kind of neural network sorts of techniques have been around since the 40s. And people have been using computers to try to classify data for, well, this is like now 70 years, okay, all right. And these techniques were kind of successful. So back in the 1980s, when I was a postdoc at Caltech, I would go and talk with John Hopfield. And at that time, they had simple artificial neural networks with, maybe 40 neurons in them. And they could recognize a few different patterns, and then that was it. And it wasn't very useful. But I remember Hopfield saying at the time, he said, you know, I do understand that this isn't working so well right now, but if we had millions of times the data, or trillions of times the data, and if we had computers that were 1 million times more powerful, this would work, I swear. And that's basically what's happened. Really, in the last 5 years, these machine learning techniques have really started to kick in. So now, for instance, voice recognition software, which people use all the time, works very well, surprisingly well. However, it wasn't always that way. Back in around 2000 or so, I remember MIT had the bright idea of replacing their telephone operators with voice recognition software. I mean, MIT, you know, it's an institute of technology, so there are always these extremely enthusiastic engineers there who want you to do the latest possible thing. So, for example, who here has been to MIT? Visited, right. Okay, so if you come in the main entrance on Mass Avenue, there is an automatic door there. And it's the world's oldest continually functioning automatic door, which means it's frequently broken, right? And similarly, this voice recognition software, it would, you know, it used to work fine when there were people doing this, but as soon as they installed this, then for the next 5 years, the following would happen. You call up and you'd say, the voice would say, whom would you like to speak with? I'd like to say, I would like to speak with Jane Smith. And the voice would say, now ringing Mary Lefkowitz. If this is not the correct number, press 9. Beep. Jane Smith. Now ringing Hua Zhang. Beep, 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 beep. It lasted for a long time. It just didn't work very well. But now, because of advances primarily actually in deep learning circuits, it works quite well. And let me explain how this works and how it works, and I'll give some indications why it works. So what's an example of a classical learning network? I'm going to give an example called a Boltzmann machine. These were invented by Geoffrey Hinton and by John Hopfield, again, back in the 80s. And it's a very physicsy kind of example. The idea is it's a network, okay? It's got a visible layer where you present the data. It's got a classifier layer. Then it's got a bunch of hidden layers. And the way that this network works, as I say, it's a very physicsy thing. This is just really an icing model. So each node in the network corresponds to a bit, which could be thought of as a classical bit here. We're going to make them quantum mechanical in a little bit. Well, I mean, here they're already looking kind of quantum mechanical because I've got Pauli matrices. It's got a Z bias term. And then each link represents an icing like a ZZ coupling, which could be ferromagnetic or antiferromagnetic. And you have a Hamiltonian, which is just the sum of all these terms. And these are weights. These energy terms here we call weights. So this is an icing model with tunable weights. And this particular Boltzmann machine is arranged with a particular fashion. It's got layers, and each node at a particular layer is connected to every node at the layer below and every node at the layer above, but not to any nodes in the same layer. And so this is what's called a stacked, restricted Boltzmann machine. Stacked because it's got layers, restricted because there's restrictions on the connections here. Okay, now these devices, and the idea, your goal is to, remember, if your goal is to, let's suppose you're doing supervised learning, your goal is, given a whole bunch of data, pairs, D and C, is to tune the weights so that when I put a new piece of data encoded in bits in this visible layer right here, and let's say this is a bit encoding of a 7, then the little 7 light or spin says, yes, this is a 7. This is a 7. I believe this to be a 7. All right? So that's how this is supposed to work. Actually, this works very well. Now, why does this work? And these, when you make larger and larger versions of these, they work for looking at very complicated and almost arbitrarily complicated patterns, which, by the way, is almost miraculous. If I take a complex system, such as this one, with many, 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 many weights, some complicated kind of connections between these weights, and my goal is to tune this. Oh, I'm sorry, I forgot to say something very important. You're trying to tune this so that the lowest energy state, the ground state of this system, or the lowest set of energy states, the low temperature states of the system, that they reproduce the statistics of the data. And usually what you do is you adjust these weights by some kind of gradient descent sort of algorithm, and you find some local optimum. Now, my intuition about local optima on complex landscapes is that most of them are bad. But it's a fact, an empirical fact, that when you have large enough networks and you tune them, then most of these local optima are actually very good, which is amazing. Why is that? This is actually a largely open question in classical machine learning. You know, people train these networks and they do very well. Why? Why should the local optima be close to the global optimum? There are lots of proofs that this is the case, but if you look at the proofs, they typically come with a whole bunch of assumptions, which are labeled things like A7P, A16U, A5P. And what the A means assumption, 5 is the number of the assumptions. They don't even tell you what the assumptions are because there's so many of them. But the P and U stand for plausible and unplausible, or implausible. And all the proofs that deep learning works have at least one unplausible assumption in them. So I'm not sure if they're actually proofs. Okay. So, but why should we expect this kind of device to be able to encapsulate or find all kinds of patterns? I claim that this comes because these networks are computationally universal. I can set up these couplings so that the ground state of the system encodes a logic circuit. For example, and I'll do it in the following way, that it's going to encode this circuit by, I'm going to have the input to the circuit up here, and then the output down here. Or I could also have the input here and the output there. So we're going to try to enforce logical relations between the different layers, and information is going to flow through either from top to bottom or from bottom to top. So how does this work? Well, let's say the information is flowing from top to bottom, so I want to make a logic circuit that takes the information at the top, at the classifier level, and produces some arbitrary Boolean function at the bottom. So I can enforce, for instance, a NOT operation if I've somehow set it so that this node is going to be a value x, which could be 0 or 1. Then with an antiferromagnetic coupling, this node will have to be not x if we're in the ground state of the system. Or if this node has been enforced to be x and these are ferromagnetic coupling, then these both have to be x. And it's a fun exercise to convince yourself that with the right individual terms and the right kinds of couplings, you can set up a, come on. Oh, poo. I'm not sure why this, okay, there we go. Because this is my lifelong love-hate affair, mostly hate with computers. My feeling is I design computers, I shouldn't have to use them, particularly the ones that I design. So you can set it up so that if you enforced the bits at one layer to be of particular values, then the bits at the next layer are going to take on some logical function, a Boolean logical function of the bits at the previous layer. And so the icing interactions will enforce the low energy states to implement arbitrary flow-through logic circuits from the data to the classifier layer and vice versa, which means that our Boltzmann machine can enforce any computable relationship between classes and data. This, by the way, is, you perhaps know that finding the ground state of an icing model is NP complete. This is a result from Maharona from the 1980s, I think. I've just sketched you a proof of why it's NP complete. If I say the question, I fix the output and say, is there any input that will actually give me this particular output? That's clearly an NP complete question for an arbitrary logic circuit. And this says that if I put energy penalties that say the output is a particular value, then my question is, what is the ground state of the system, which is, what are the inputs that actually give you this output? So this tells you that finding the ground state of an icing model is NP complete, which is another reason to be suspicious of the notion of why these devices, why can they actually find the right answer? And the answer is, I don't know. Okay. So our goal, again, is to find these weights so that the probabilities And this is why it's called a Boltzmann machine. We have these Boltzmann factors here. The thermal probabilities, typically at low temperature or high beta, for these classifier data pairs match the frequency of them in the data. That is, we're trying to construct a physical system whose Boltzmann distribution matches the probabilities of the data. And the way that you typically measure this is that if Q are the actual probabilities and P are my machine's estimate of the probabilities, we try to minimize the relative entropy between the actual distribution and our constructed distribution. And this relative entropy is actually the free energy of this system. It's not hard to show. So we're trying to minimize free energy on a complex landscape. And the way that this learning works is typically it actually works by stochastic gradient descent on the weight space using backpropagation, which simply means that you adjust your weights, you see how you're doing, you look in the vicinity of the weights that you have, you find better weights, and then you go downhill. Backpropagation means then you go back and periodically and you readjust them. There are other methods called Gibbs sampling, again, because you're sampling from a Gibbs distribution. One is called Contrastive Divergence. This is actually a very fun, there are a whole bunch of these techniques. Most of them, again, were developed back in the 80s and 90s, and only now are actually proving useful. So for those of you who are jealous of the people who are now making 7-figure salaries for having gotten their PhDs in classical machine learning, you're wondering why am I doing quantum mechanical stuff right now, no doubt. Remember that many of these people just were kind of wandering in the wilderness for decades saying, this will work, and people say, oh yeah, show me. They said, well, it will work, okay? But now it does work. This is a particularly fun, I think I'll tell you about this because I do have time. This is a particularly fun version of how it works. Here's a picture of how people learn and establish memories. This is the cortex. Again, don't you like my picture of a brain here? Right, this is the hippocampus with a little area in the brain. And while you're awake, you're taking all these inputs that get processed through the neural circuitry of the cortex to set up feedback loops with the hippocampus. The synaptic weights are being established during this time. Many, many, many synapses are being formed. When you go to sleep, the internal inputs no longer come in. And what happened is, but these feedback loops between the cortex and the hippocampus are still going like crazy, reinforcing each other. And interestingly, removing synapses. Basically, 90% of the synapses formed during the day are being removed at night while you establish stronger but more parsimonious neural pathways while you're dreaming. And then, actually, interestingly, what happens, most of the dreams that you remember are during rapid eye movement sleep, which is a relatively shallow form of sleep. When this happens, these feedback loops get disrupted, and all kinds of memories start getting mixed up with each other. So, you have a memory, I have dreams where I open the door to my apartment in Oxford, and I'm suddenly in my apartment in Cambridge. And this is completely normal, okay? Nobody thinks twice about this. Okay, and these are your dreams. And actually, you can train neural network circuits very successfully in this fashion. Why does it work? Okay, nobody really knows. I mean, my intuition tells me this ought not to work. You're exploring a complex energy landscape. You're finding local minima by stochastic gradient descent. And then it turns out almost all these minima are really good. And it's really not known. I actually, if anybody, this is something I'm doing a lot of work on right now. If anybody wants to talk about this later, I can give you a list of the different approaches to showing this is the case. I mean, I don't know. Maybe the problem can be divided into logical subtasks, and doing better on a subtask has a detectable effect on the overall performance, and then doing better coordinating subtasks has a detectable effect on performance. Maybe that's what's going on. That's kind of how human beings do things. But we don't know how these deep neural networks are actually doing this. At any rate, if the gradients are small, you have lots of data, lots of layers, lots of time, this works well. Okay, now let's look at deep quantum learning. All right, the first thing is that we can actually just take Ising Boltzmann machines, and we can replace stochastic gradient descent with things like Grover's search. Nathan Wiebe at Microsoft has a nice paper on this. Or we can do quantum annealing. The folks at D-Wave are actually using their D-Wave devices. They're tunable Ising models. They're perfectly set up for making deep learning networks on Boltzmann machines. So the deep network is still classical. We could look at a quantum weight discovery process. Well, that's interesting, but what we'd really like to have is something more quantum mechanical. By the way, these methods work pretty well. D-Wave devices work quite well as Boltzmann machines. They find nice patterns, solve problems. But remember what was important about the classical networks is that they are universal. There are weights assignments that allow them to do any classical computation that you want. Indeed, if they were not universal, that wouldn't be useful. If you couldn't actually program in and, or, not, and copy operations, then these things couldn't compute their way out of a paper bag, and you wouldn't expect them to find complicated patterns, because they'd only be able to find some very small subset of computable patterns. So now let's actually look at universal deep quantum learning. Why? Well, because deep quantum learning already sounds cool, and universal deep quantum learning sounds even cooler. But actually, there's a good reason, is that if we really want to have quantum networks that can actually find patterns that you can't find classically, we want to take advantage of the fact that they can perform quantum computing. So we'd like these networks to be able to perform universal quantum computing in the same way that the classical networks can perform universal classical computing. Oh, and by the way, the classical neuromorphic networks are also classically universal. Universality is very important. So, and then we'd like to make it very quantum mechanical, we'd like to adjust the weights and learn our quantum circuit quantum mechanically. So how do we actually make a universal deep quantum learning network? Well, there are many possible ways. I mean, a quantum computer itself is a deep network. And the weights are just the simple assignment of logical gates in the network. And then you say, oh, well, I'd like to construct a particular quantum circuit that will perform a particular task, which, of course, in general is an NP-complete problem. But let's do this in this Boltzmann-like machine context. So it turns out that if we add tunable hopping terms to make this into a Heisenberg model, so I'll make this little dotted line right here, which says that if I have a 1 here, the 1 can hop over here. If it's over here, it can hop over there. Then it turns out that these networks can now be made universal for quantum computing. This is a paper of mine with Barbater Hall from a few years ago in Nature of Physics. Both as a Hamiltonian quantum computer, so a dynamical system, and also in its ground state. I'm going to describe briefly how this works. This is actually kind of a funky method for doing it. Here's my network. I haven't actually drawn in all the links, but the way that these links work is that you have these hopping terms going down here. You can imagine this being a bunch of particles that start up here, and then they can hop down here, and then you have Ising-like couplings going along this direction. And so where they can hop is a function of how they hop is a function of their neighbors. And you set up a kind of a string of particles. So if this particle was here, it can only advance here if it has 2 neighbors that are right here. So it's like these particles are holding hands as they move through this computation. And these particles carry qubits, and we could say this is the state of the qubits on some kind of space-like surface here. And as this surface moves through the computation at the end, then we find that, this is at the beginning now, I'm sorry. If they go through the beginning, they move up in this direction. When they get to the end, you can set this up so that this now tunable Heisenberg model is capable of universal quantum computing. And this actually turns out to be closely related to the Wheeler-DeWitt equation of quantum gravity, but I won't actually tell you why, because Enrico tells me I don't have much time. Okay. But if you want to find out how it's related to quantum gravity, I'll happily talk with you after this. Okay. I'm very tempted to tell you now, but I'm not going to do that. Okay. So now let's look at a universal quantum Boltzmann machine. Let's imagine we have such a device, and now we're given classical data. classifier data with classifier labels. Probabilities for this would be supervised learning. Of course, we can use this for unsupervised learning as well. We want to train the weights of our Hamiltonian so that our Boltzmann distribution, or even the ground state of the system, approximates the statistics of the classical data. So our low energy sector of this Hamiltonian generates and classifies the patterns in the data. See, now because we've set it up so that this system is universal, we can imagine tuning these weights. So let's say that this is the data level and this is the classifier level. We can set up the weights so that when the process by which the system is this quantum learner is trying to classify the data is a quantum computation whose input is a bunch of data, say just zeros and ones, which is a program for this universal circuit. And the output, you go through a quantum computation, and at the output, here up at the top, the output of the quantum computation tells you what the classification of the data should be. Now here, because we have these well, it's well known that shallow quantum circuits or even deep quantum circuits can generate patterns that cannot be generated classically. Right? This is what's called, goes by the kind of hideous name of quantum supremacy, horrifying name, all right? But it means that if I have even a relatively small quantum device that can generate patterns that can't be generated classically, here we're trying to do the opposite. We're trying to take a small device and ask, can it recognize patterns that can't be recognized classically? And actually, if the data is being generated by some quantum system, for instance, if this is actually a quantum state rather than just classical data, the answer is yes. But in general, what we'd really like to know is if we have classical data like we're trying to recognize a voice, we're trying to find patterns in some large data set, we're trying to find out what happens to your brain on drugs, we'd like to be able to do something better on a quantum computer or with quantum learning than we can classically. So I call this process, so quantum supremacy is quantum systems generating patterns in data that can't be generated classically. The opposite procedure, which is, we don't even know if this works, by the way, but we would like to show it's possible, is a quantum device recognizing patterns that we can't find in data. If we could do that, I would call this supreme quantum learning, which sounds much better than quantum supremacy. I mean, supreme quantum supremacy sounds like, us quantum people are going to go and burn classical computers or something like that while dressed in masks and robes and stuff. Whereas supreme quantum learning sounds like a particularly tasty dessert with lots of ice cream, chocolate, and more cream on top. Okay, so examples include, can we learn a quantum Fourier transform? So given some training set, can we learn it? Boson, this is, so, and there is evidence out there that we ought to be able to make learning networks that can learn to do some simple quantum algorithms, like, for instance, Simon's algorithm. Jake Taylor and company have a paper on that. Boson sampling, we have here's non-universal quantum information processing. We pop in a bunch of zeros and ones into our array of beam splitters and interferometers. Here's our classical statistics of the output photons. This is famously exhibits quantum supremacy. So supreme quantum learning is, suppose can we do it in the opposite fashion? We're given the statistics, we pop it in here. Can we adjust these weights here to make the proper patterns of zeros and ones come out there? Could a deep quantum learner learn how to factor? Could it learn Shor's algorithm? Somehow I doubt it, but maybe it's possible. And the primary question is, and this remains an open question, is can deep quantum learning reveal useful patterns in classical data that classical computers can't? And with that, I'll stop. Thank you very much.
Okay, is there questions?
Could you speak a little bit about the quantum gravity you mentioned?
You really want to? Okay, sure. Why not? Yeah, so the Wheeler-DeWitt equation is an equation that says it's the equation for the interaction of quantum fields with quantized gravity. And it's very simple. It says H psi equals 0. where H is the Hamiltonian for both fields and gravity. Now that actually looks like a pretty bizarre equation for the universe because stuff is happening. You know, I personally do not feel myself to be in an eigenstate of the energy. I don't know about you, but I don't. And so the way that this actually works is if you solve the Wheeler-DeWitt equation, then let this line here represents a space-like surface, okay? And then normally the evolution evolves quantum fields from space-like surface to space-like surface. And here, what's happening is the actual dynamic Hamiltonian of the system will evolve the system forward into a superposition of different space-like surfaces. I'm drawing another right here, but this is one possible space-like surface. And then on that particular space-like surface, you have the correct quantum state for the fields. H psi equals 0 means that psi is actually a sum over all possible space-like surfaces. This is labels one of these space-like surfaces, correlated with the correct state of the quantum fields on that space-like surface. So the ground state of this system is a superposition of all possible histories of matter fields and the gravitational field. This, by the way, it's related. This is what's called the Margolis Hamiltonian. It has this nice many-fingered time that the surface can move forward in time in different places, like different fingers moving forward. I tried this out. The original version of this is the Feynman Hamiltonian, which has a single clock. And the ground state of the Feynman Hamiltonian for quantum computing is a superposition of all possible clock states together with the correct state of the qubits in your quantum computer at that time. In 1994, 1994, I was hosting John Wheeler at Los Alamos, and I described this construction to him with the Feynman Hamiltonian. This was a long time ago, right? I mean, this was, and he said, oh my, I said, look, it's just like the Wheeler-DeWitt equation. And he said, it's exactly the Wheeler-DeWitt equation. Of course, Wheeler would say pretty much anything, like, you know, that visit he came to give the physics colloquium. Did anybody ever see John Wheeler talk? Yeah, okay, yeah, he had these transparencies with, like, you know, the universe looking at itself and, like, it from bit and stuff like that. It was completely crazy. And when he was giving his talk at Los Alamos, he was walking up the steps to the stage, and he dropped his transparencies everywhere. And I was his host, so I said, oh my God, I'll help pick them up. I said, here, can I help you sort them out? He said, no, it's okay. And he just gave the talk in whatever order he'd picked up. And the amazing thing was, it was completely indistinguishable from any other talk he'd given. So his talk was actually permutation invariant, which is a remarkable thing.
Okay, yeah. You want to try again with the microphone?
So thank you for your talk. I loved your talk. In this instance, is it possible to have more than one answer?
Oh, sure. Absolutely. Because it's quantum mechanical, right? So you can get a superposition of answers at the output.
So given that you can, how does a practitioner arbitrate what is the right answer or the one that is correct or verifiable, whatever, pick your...
Well, you know, this is the funny thing about all machine learning kinds of things. You know, as I say, with deep learning, there's no proof that deep learning works. And for a long time, it didn't work very well. But then, you know, kind of when we didn't have not just computers that were, you know, computers are now 1,000,000 times more powerful than the ones in the 1980s. Even my, you know, this computer is like a Cray supercomputer. And we have trillions of times the amount of data, and now this works. And this is an empirical fact. So a lot of these machine learning things are you just make a device, you try to recognize patterns, you see if it's doing a good job or not. You try to be, you know, responsible about the statistics that you use to determine whether it's doing a good job or not. I mean, typical statistics are things like, I mean, because many of the people who developed their physicists, you use this relative entropy, Kullback-Leibler distance between your actual statistics and your estimated statistics. Yeah, but in my quantum device will also produce probabilistic outputs. So these, I could just have the same thing. This is my classical data. These are the probabilities from my quantum device. And then you try to see if that works out. I actually think in deep learning, I mean, it would be nice to prove that deep quantum learners can do a better job than classical learners on interesting data sets. I think that the best we're going to do is to prove that they can do strictly better than classical learners on data sets that are generated by quantum mechanical systems. Because of quantum supremacy, we know that a classical deep network cannot generate the same statistics that are generated by a deep quantum network. Whereas a quantum network, of course, can generate those statistics. So then we might be able to prove that the quantum network will indeed converge to the right answer. But what would be much more interesting if a quantum network could find patterns in, for instance, financial data that a classical system can't. And I don't think we're going to find the answer to that until we actually build these devices and see what happens. Luckily, we happen to live in an era where people are building these devices and trying them out, so we probably are going to see what happens.
Okay, so I will allow me to make just the last question, sorry, because the time is running. So Seth, you have shared with us your disappointment and even your deception when you just faced this field 6 years ago, in the sense that all the keywords are sounding like deep, intelligent, and so on. And yesterday we had a round table, so I profit now that make a post-deadline question. What prevents us from reaching to fabricate out of inanimate matter truly intelligent devices? Or you give examples with the brain, but what prevents us from creating emergence of intelligence or consciousness? And I'm speaking about truly macroscopic biological systems, but also even at the level of a cell, self-replication, and all these kind of phenomena. How far we are? What prevents us? It's the wrong path, or what? It's just a size, as Hopfield said. It's a question of data.
Gee, well, I would say nothing prevents us. And in fact, in terms of making models of self-reproducing evolving systems, people have been doing that for a long time, right? I mean, this is the field of artificial life, where you make little artificial
But just at the software level, let's say.
Well, so I mean, I'm not a big, there's this worry popularized by Elon Musk and the late Stephen Hawking that artificial intelligences will take over the globe and, crowd human beings out. I think this is something to worry about, but it's not about to happen right away, because right at the moment, the fact that machine learning devices are getting better at pattern recognition doesn't mean that they're getting better at doing a lot of other things. Indeed, when you look at people's efforts to try to build self-driving cars, you see that, which requires a much broader spectrum of techniques, even though I personally find that when I get behind the wheel, my IQ drops by 40 points. This turns out to be a very hard thing to do. So I actually think that it's quite likely that in the future we'll have machines that we regard as being intelligent or perhaps even conscious. I just don't think that day is right now. Because it's a complicated
because
problem.
of size of data, because of ideas, because of algorithms?
I think, yeah, actually, I think it's about it's about software. It's not so much about hardware. Computers are getting very, very powerful in terms of their hardware, approaching, what human beings do. They're not there yet. I mean, this says my brain has billions of neurons and trillions of synapses, tens of billions of neurons and, tens of trillions of synapses. That's more components than the largest classical computers. But I mean, classical computers will be getting there relatively soon. But programming is hard. Your brain, my brain, is the product of millions of years of evolution, and human language and social systems and what we regard as being human is the product of hundreds of thousands of years of evolution. And this is a very, very long feedback process in working out ways to behave and not, and it takes a long time. And you may have noticed that software, hardware has improved a lot, whereas software has gotten worse. Like, for instance, Microsoft, and why is this? It's because every time software designers design a new generation of software, they assume the hardware is going to be twice as good in 2 years' time, right? But then they always err a little bit and make their software demand a little more than twice the amount of computing power. So for example, Microsoft Word has gone steadily downhill since 1995 as people add more and more bells and whistles that you just have to turn off. And it's not that the computers have actually gotten faster. I mean, you know, they do the same things. They do it slightly slower, and they're doing much more information processing. But I think the process of getting artificially intelligent entities, computational beings, I'm sure we'll get there, but I think it's going to take a long time, comparable to amounts of time in human cultural and social evolution. It just takes a long time to do that stuff.
Hope we are alive there. Thanks a lot.
Thank you.